Welcome to the online seminar Quantum Leap, Exploring the High Energy Universe. It's a pleasure to have you here to this event, which is organized by Nordita, the Nordic Institute for Theoretical Physics, and Fysikum, which is the physics department at Stockholm University. And this series, Quantum Leap, it was launched this year, particularly because the United Nations proclaimed 2025 as the International Year of Quantum Science and Technology. And this has also been promoted by UNESCO. And this event is also timely because the Nobel Prize in Physics this year was awarded to an experiment which showed how quantum leaps or tunneling can occur on a macroscopic scale. And in today's event, we will explore one of the most important frontiers in physics today, which is the high energy frontier. This is a research area that happens on several fronts, from particle collisions that happen deep inside the tunnels at CERN to gravitational waves that reach us all the way from distant reaches of the universe. But it's not only about experiments and observations, it's also related to the fundamental interactions of nature and how we understand them. And for that, we need to develop new theoretical techniques. So in this seminar, we will explore both the experimental as well as the theoretical side of the frontiers of high energy physics. And the event format will be that we will have 15-minute presentations by our panelists, which include, let me go to the next slide, Frank Wilczek, who is with us today here from the US. He has been awarded a Nobel Prize in Physics in 2004 and has a very illustrious list of affiliations, including Stockholm University, MIT, the T.D. Lee Institute, the Wilczek Quantum Center, Shanghai Jiao Tong University, and the Arizona State University. We also have Sara Strandberg, who belongs to Stockholm University, or not belongs, but is affiliated with Stockholm University, Oksana Iarygina from Nordita, and Oliver Schlotterer from Uppsala University. And after we have listened to their presentations, we will have a joint discussion. And it's possible to ask questions during these talks. We might have one or two questions after each talk, but we will also have a selected number of questions during the joint discussion for the panelists. And it's not possible for the audience to share screen or to talk in the chat to other members, so it's only us, the hosts and the panelists, that will see the questions and what you write in the chat. And we will also record this event, but the only ones who appear in this recording are the panelists and me. And finally, I'm Jonas Enander. I'm a science writer and communicator, and I also have a background as a researcher at Stockholm University. So with that being said, it's time to move forward to higher and higher energies, and we will start with our first speaker, which is Nobel laureate Frank Wilczek.
Okay, well, very happy to be with you virtually from Concord, Massachusetts. It's a bit early for me, so if I seem unusually incoherent or just incoherent as usual, I have at least a bit of an excuse. High energy physics, I've been asked to give a historical perspective on high energy physics. And the first question is, what is high energy physics? And one could come at that from very different perspectives. MEV in different contexts can mean milli-electron volts or mega-electron volts, for instance. But I think the traditional usage is that high energy physics evolved from what used to be called particle physics, and it's the continuation of, and I'll argue the culmination of the grand program of understanding what matter is by reductionism. That is, by studying how very small things interact with each other and then building back up. So it leans on the idea that the laws apply that you discover it somewhere and somewhen work everywhere and everywhen, and also that the laws are local, that you can understand things building up from the local interactions to what happens on larger scales. And the good news, I think the most important legacy of this enterprise has been to really understand what matter is in a profound way. And we have very precisely defined, very complete theories of what ordinary matter should be that are extraordinarily beautiful, based on symmetry and the profound insights of quantum mechanics. So we have a mapping of the real world onto a world of concepts. A theory is the more impressive, the greater the simplicity of its premises, and the more it relates. And by that standard, our understanding of matter is remarkably successful. You can write a short computer program that has a few numerical inputs and outputs the material world. So would output, for instance, the periodic table, the masses of nuclei and other hadrons, and it's a fantastic achievement for humanity, culminating this program of understanding nature by analysis of small pieces and then synthesis to build up from there. So already in the late 1920s, Dirac, after the mature version of quantum mechanics was in sight, including quantum electrodynamics, was able to claim that the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known. Since then, this has been vindicated. We still use the principles of quantum mechanics and with some supplements, the same principles of quantum electrodynamics that Dirac was alluding to here, but the large part of physics has expanded a lot. Now we understand also what goes on inside atomic nuclei, inside stars, and so forth. The great inspiring lesson that came out of this enterprise is that symmetry rules. The way nature works is by laws of fantastic generality and also mathematical symmetry and beauty. I'll just, without explanation, say of what this is. I'll be happy to explain in detail in response to questions, but the enterprise of high exploration at accelerators and cosmic rays and unearthed a whole plethora of particles, and it turned out that one could get a description of these particles that is based on high symmetry. The interactions, this is a mathematical representation of SO10. So we have a gauge interaction that governs the exchange of vector bosons that generates the strong, weak, and electromagnetic interactions, unified into a larger structure. Very nicely, the particles that actually exist match precisely the so-called spinor representation of SO10. So you can summarize what we've learned about the world is that it's rational, can be understood, and that understanding is corresponds to mathematically precise and beautiful structures. This program is not quite complete. In fact, one might say it was abortive. The climax I was hoping for in this was in that unified theory, you get an indication that the different forces of nature should unify at very short distances. The different coupling strengths all come together as they must to make a unified theory. But it only works quantitatively if you include supersymmetry at a low scale. So this was a tantalizing hint that supersymmetry should show up as something like TeV scales. And so far it hasn't. But maybe that's for the future. Okay, so that's a legacy of fantastic success. But what's next? And I think the second part of the program of analysis and synthesis is the synthesis part, building up from the knowledge that we have from that foundation. And of course, going back to Dirac, you could say that all of chemistry is a matter of exploiting the laws we know, and not to mention engineering and so forth. But it's been there are two comments to make, I think, that are timely in this regard. One is that Dirac qualified his statement at the time by saying that the difficulty lies only in the fact that the application of the laws leads to equations that are too complex to be solved. We've made a lot of progress with the help of our silicon friends in being able to solve the equations. And that's still a frontier of physics, solving the equations that we now know govern what matter is in more and more complex situations to describe the material world, both for our own use and also to understand what's out there in the sky. Let me give one example that uses the relatively modern understanding of matter, high energy physics in the usual sense, where there's been recent dramatic progress. We'd like to understand, we have the equations to understand how matter behaves in the very early universe and at very high density. So in neutron stars, for instance, on the basis of QCD. We have a profound theory of how stars work, ordinary stars, but the knowledge of how neutron stars work is relatively primitive. And we also would like to understand quantitatively how the early universe worked, whether there are phase transitions associated with matter cooling off from extraordinarily high temperatures to lower temperatures. What are the signatures of those things? And just explore matter that's made out of not just electrons and photons and ordinary nuclei, but in more extreme conditions. And this is a conjectured phase diagram for QCD as a function of temp for the world as a function of temperature and density with different physical regimes here. And this has been explored in so-called heavy ion collisions. And there's reason to believe, theoretically, that there should be a critical point where this is analogous to the triple point, not the critical point of water or many other material systems, where you have a solid and a liquid phase, and at the critical point, the distinction between the solid and the liquid phase goes away, or the solid and the gaseous phase, I guess, in some cases. So there, at the critical point, there's a beautiful, elaborate theory of enhanced fluctuations, so-called critical opalescence, and that might give us a way to see if these theoretical ideas about the description of matter in extreme conditions are realized in nature. And very recently, there have been indications, not yet entirely decisive, but remarkably structured and detailed and intricate, indicating that at the appropriate density. You can scan different densities by looking at nuclear collisions at different energies and different impact parameters. And there's a lot of analysis that goes into this. But the long story short is that it appears that under the right circumstances, you can have the fireball that results from a heavy ion collision pass close to the critical point as it cools down, and the fluctuations imprinted themselves into the final state. And that seems to be actually what's happening, and we have a tentative identification of the critical point. This is timely because gravitational waves are opening up the interior of neutron stars to investigation, and we need to have a theory ready to describe those observations. And this is going to be an exciting thing in the foreseeable future. Gravitational waves can also tell us about phase transitions in the early universe, which is another frontier of high energy physics. Okay, so exploitation is one frontier. Another is continued exploration. We're not done yet. We're missing most of the universe in terms of mass in our description of matter. We still don't have a really satisfactory understanding of how gravity fits in with the other interactions, although it's not as bad as usually portrayed. And there's still a room for exploration. Many directions are being explored. Of course, you'll hear about other ones in the talks that follow, but I'm just going to give you a very biased sampling of something I've been particularly interested in for a long time, and that is really a heady ferment at present. That's the physics around axions. So I won't have time to discuss in detail the motivation for axions. It's a long and intricate and profound story that brings in time reversal violation, anomalies, high symmetry, and both known and postulated. But the long story short, I always wanted to name a particle after this laundry detergent once I saw it on the supermarket racks. And when we have a particle that cleans up problems associated with the structure of the standard model, the temptation was there, and the stars aligned, and now we have this remarkable particle that people are looking for and could very well supply the dark matter of the universe. This is how axions get produced. You start it in everything I've been talking about. The framework is quantum field theory. So we need a quantum field in which the axion sits, and the axion is the phase variable. So it's the angular variable here associated with a complex field. And there's a special kind of symmetry associated with rotations in this direction that the axion was built to implement. And at high temperatures, the fluctuations are such that the average value of this complex scalar field, this order parameter, is 0. But as the universe cools, it falls down and eventually reaches the bottom of the potential. So this sombrero is slightly tilted for reasons that are too complicated to explain right now. And what happens is the axion field, the angular field, then slowly settles down to the minimum, and we have residual oscillations. The reason we have axions is kind of a theory of evolution that explains why the time reversal violating parameter theta in the strong interaction is so small observationally, which would otherwise be very mysterious, the axion field basically is promoting that variable to a dynamical variable. And then we have a theory of evolution for why that very dynamical variable should settle down to a very small value. And the thing that makes this ripe for experimental investigation and makes it really compelling is that although the axions were introduced in an attempt to solve a mystery in fundamental particle physics, or that is why this parameter is so small in nature, which is otherwise very mysterious. So it by dimensional analysis should be 1. In fact, it's less than 10 to the minus 10. So there's some explaining to do. We get this axion field. We have the theory of evolution, and there are small residual oscillations. However, it doesn't settle down to exactly 0. We have damped oscillations, but they don't damp exactly to 0 in the history of the universe. And it turns out that as a very unexpected bonus of this solution of a problem in fundamental physics, you have residual oscillations, although that they're very small, and they were designed to be very small. So, well, that's the virtue of the theory, is that they're very small. Nevertheless, because the fields involved are so stiff, carry so much energy, the energy in those oscillations is enough, is the right kind of value to provide the mysterious dark matter of the universe that astronomers need. So the question becomes, is that really the dark matter? And this can be probed experimentally. The schematic idea for many of the searches is, if you have an axion, the fundamental theory predicts that it should couple to 2 photons in a particular way, and if and that means that if you have an external magnetic field, an axion can convert into a photon, and that photons are things we know how to deal with and observe in many ways. And since we don't know the precise mass of the axion, theoretically, we don't know even that it exists, but if it exists, we don't know its mass. We need to have, well, first of all, we need to encourage axions to convert into photons. And it turns out that using appropriate metamaterials, you can do that. And that's been a tremendous enterprise in recent years, including important work at Stockholm. And this makes a very pretty picture. This is, you need, since you want to be able to use resonance to enhance the signal and make the axions convert into photons. And you don't, it's like tuning a radio, but you don't know the frequency when you don't know the mass. And so you have to be able to have something that tunes the cavity, and this spiral design is one of the ones that's being explored at Stockholm and seems very promising and makes a pretty picture. So to tune the cavity, you have these rods inside, and then you tighten or loosen the array by circular motion in this spiral. So with tricks like that, using all the resources of modern physics in cryogenics, metamaterials, squeezing, exotic amplifiers, the tiny signal predicted from dark matter axions now appears to be in sight. So it's an exciting time. Around the world, people are mounting experiments to try to exploit this opening. And it's the predicted mass range, the most likely mass range for axions to provide the majority of the dark matter is this blue band, and the theoretical expectations are this gold band, and you can see the experiments now. The planned experiments are going to get there in the foreseeable future. 5 to 10 years is projected. Meanwhile, axions have been discovered in condensed matter physics. It's a remarkable feature not only of axion physics, but of other concepts, anyons, and others that have been inspired by condensed matter physics and feed back into condensed matter physics. Here, you have the same equations as govern axions, but with different meanings of the symbols occur in so-called topological insulators. And this means that you can get fundamental measurements of the fine structure constant, it turns out, because, well, this has to do with the deep aspects of quantum field theory and anomalies, and so, but it turns out that you have axion electrodynamics with a quantized value of the parameter, which depends on the fine structure constant, and this kind of effect that emerges can even be used to measure the fine structure constant, and has been, to get a 1% value. And very recently, experimenters at Harvard have even produced quasi-particles that have the same quantum numbers as the axion and obey precisely the same equations as axions and are bulk excitations. So they've actually produced something that is worthy of being called the axion quasi-particle in a specific material. And this is a growth area. So axions maybe certainly don't exhaust the field by any stretch of the imagination, but are a beautiful illustration of how many ideas come into play as we understand the world and try to move from the analysis of matter to the exploitation of matter, and bring all the resources of physics to bear on staking out new territory, as well as exploiting the knowledge we've won so far. And I think with that, I will end. I have prepared answers to questions that may occur later, but I will stop here for now. I think I've used my time, I presume.
Yes, thank you so much, Frank.
All right.
And we will save, as you said, the questions and answers. Let's save that for the joint discussion and move on with the next talk by Sara Strandberg from Stockholm University. Thank you, Frank.
Can you hear me?
Yes.
Yes, very good. Okay, let me share. And then I will make it full screen. Okay, so now you can see my slides. So hello, everybody. It's a pleasure to have been given the opportunity to present the high energy physics program at CERN and its connection to the composition of the universe, which is, of course, a very big question. So I will only be able to touch a little bit upon that in this presentation. So as Jonas said, I'm Sara Strandberg. I'm a professor in experimental particle physics at Stockholm University, and I am also a member of the ATLAS experiment at CERN. Frank said that high energy physics kind of developed from the field of particle physics. And I would say that this transition essentially happened when the particle physics community started to exploit the particle colliders which had been developed, because this gave us a tool then to not only study the particles that we have around us in our ordinary kind of world, but also create new particles from pure energy in the laboratory. And what we exploit here is the fact that you can take any boring, cheap particles like protons or electrons, and you can accelerate them up to very high energies. And then you can use the kinetic energy of these particles as you collide them to turn that into mass of new particles. So instead of with kind of boring car collisions as you have here, where the cars just break up, here instead you collide boring cars and you make new fancy cars that weren't there to start with. And this is all possible. This kind of magic of particle physics is possible thanks to the energy mass relationship, EMC squared, and the wonderful laws of quantum mechanics. So these particle colliders, they actually enabled us to find and study also short-lived particles that do not make up kind of the stable component of matter. And as we started making these experiments, actually, it was revealed that the the subatomic world was much, much more complex than anybody could ever have anticipated before these experiments took place. So just to put things in perspective, here you can see how the energy frontier has evolved over time. So since we started using particle accelerators in the 1930s or so, here you can see that the collision energy has increased by a factor of 1 million or so. And now we're at the LHC, which is the current energy frontier in the world. It's CERN's flagship project, and it stands for the Large Hadron Collider. And at the LHC, we collide protons together with a collision energy of 13.6 TeV, a number that I will very soon put in perspective. So this high energies can only be reached by a very large accelerator. So the LHC is 27 kilometers in circumference, and it's located 100 meters underground on the border between Switzerland and France. And in this Large Hadron Collider, we accelerate protons up to 99.999999% of the speed of light. And this means then that every proton will carry a kinetic energy of 6.8 tera electron volts. And that actually is equivalent to the kinetic energy of 13 flying mosquitoes, which doesn't sound like a very big number. But if you think about how many protons and neutrons and electrons you need to make up 13 mosquitoes, it's actually pretty impressive to be able to condense all that energy into one single proton. And in fact, the kinetic energy of these protons is about 7,000 times larger than the mass of the proton. So really most of the energy of this object is contained in the kinetic energy. And by colliding these two protons together, you can then form new particles that could be as heavy then as 14,000 times the proton mass. These very high energy collisions also allows us to probe very small length scales, so we can see if the particles that we collide, for instance, if they consist of smaller constituents. And we can probe length scales down to about 10 to the minus 20 meters. And the energy density and temperature in these proton-proton collisions, they correspond to the conditions in the universe about a picosecond or so after the Big Bang. So we can really study processes that then potentially happened in the very early universe. And of course, this is a very complex machine that you need in order to get this high energy. So you have these superconducting radio frequency cavities that do the acceleration, and then kind of the very big part of the LHC engineering goes into these very strong dipole magnets that keep the protons in a circular orbit as they move around the accelerator. These also need to be superconducting, and they're cooled with liquid helium down to only 1.9 Kelvin above absolute zero, which is actually colder than outer space. But these high energies then gives us the possibility to produce potentially heavy new particles. But we also need to be able to study very rare phenomena, because many of these new particles that we look for are not so common to produce. So therefore, we collide actually not single protons with each other, but rather bunches of 100 billion protons. And we collide these bunches of protons 40 million times a second, which gives us a very large data set then from which we can kind of study what actually happens in these collisions and look for rare phenomena. So with the LHC and all the accelerators that that we had before the LHC, we have now built up this standard model of particle physics. So we know that we have these fermions in the first generation that are the stable components of ordinary matter, the up and down quarks and the electron. But we also have these heavier fermions that, because they are heavier, are unstable, but we can still produce them and study them. We have the gauge bosons that mediate the fundamental forces. So for instance, the photon is the mediator of the electromagnetic force. We have the Higgs boson that we found in 2012 that explains how the particles in this theory get their masses. We also know that most of these particles have antimatter partners, not all of them, because some are their own antiparticles, in fact. And we also know that all of these particles that I described actually together affect the properties of matter. So it's not enough to just study the kind of stable components of matter, the up and down quarks and the electrons. We need to understand how all of these particles behave in order to really understand what the universe is made of and how it works. So sometimes you have maybe heard that the Higgs boson was the last kind of missing piece in the Standard Model puzzle. And with that, what one means is that the Standard Model with the Higgs boson is kind of a self-contained theory that you can use to make predictions. And it actually does explain, as I will come back to later, the experimental results that we have very accurately. But the important question then is, of course, if the Standard Model can explain all of the matter in the universe, and you probably already know that the answer to that is no, because we know from a lot of cosmological and astronomical observations that only 5% of the energy density or energy budget in the universe is in the form of ordinary matter, so the atoms that the Standard Model describes, whereas about 27% or so of the energy is in the form of what we call dark matter, which is some kind of matter that feels the gravitational force but does not interact with the strong force, neither with the electromagnetic force. And if you look at all the particles in the Standard Model that I showed on the previous slide, you can quite quickly convince yourself that none of them can be the dark matter. So the dark matter has to be something new. It might be one, or it might be a whole slew of new elementary particles. And this is, of course, a big piece of high energy physics today to try to understand what the dark matter is made of. Another problem that is intimately linked with the composition of the universe is the fact that we had all these antimatter particles that I described in the Standard Model. But if we look at the universe, it seems like the universe only consists of matter. So we have no real mechanism, or at least we don't have enough of the mechanisms to explain how matter has prevailed over antimatter and given us a universe with some matter that we are made of. So how do we then go about to search for these beyond the Standard Model things that we need in order to explain these unknown properties of the universe? So we can do it in two ways. So we can either do very precise measurements of the Standard Model particles and processes that we already know about to see if we can see some deviations, some cracks in the Standard Model that can tell us in which direction to move forward. But we can, of course, also do direct searches for new particles and new phenomena that are not part of the Standard Model. And at the LHC, we do both of these. And I can for sure not show you everything that we do because it's a very rich program. So I'll give you a couple of examples. So here you can, for instance, see many, many different measurements of probabilities of processes that occur within the Standard Model. So here you have all the different processes. And then on the x-axis, you can see the probability that these processes occur. And one thing that I want you to note is that actually this x-axis spans 15 orders of magnitude. So we go from very, very common processes all the way down to really, really rare processes. And in all of these cases, as you can see here on the right, the theory and the experimental result agree really well. So there is no hints here of any deviations, or at least no significant deviations from the Standard Model. So here it really holds up to the massive scrutiny. Another important arena for precision measurements is the Higgs sector, because the Higgs boson is the last particle that we have found. Therefore, it's the one that we know the least about experimentally. And one important fingerprint of the Higgs boson is that it should interact with the other particles in the theory in proportion to their masses. This is how it gives the mass to the particles. So you would expect, some linear relationship between the coupling strength between the Standard Model particles and the Higgs boson and the masses of these particles. And this is exactly what you see here on the plot. So on the x-axis, you have the particle masses, and on the y-axis, you have the coupling strength, and you can see that they all kind of nicely line up on this line. And at the bottom here, you can see the deviation from the expectation, and you can see that everything is basically consistent. But you can also see that there are quite large error bars here still. So we only have been able to do these measurements for a few particles and only with a precision of about 10%, whereas you expect maybe many of the Standard Model extensions that we look for would rather lead to deviations at the percent level, so 10 times smaller than what we can currently probe. So we also, of course, as I said, want to directly look for new phenomena. And one obvious thing that we look for is dark matter. And as I said, dark matter is a particle that interacts very weakly with ordinary matter. So if we would be able to produce it at the LHC, it would not leave any signals in our detector. So you wonder then how you can see something that is actually invisible to us. And the trick that we use is to look for something that we call missing momentum. And what we exploit here is the fact that at the protons, when they collide, they will have a large momentum, of course, in the kind of collision direction, but zero momentum in the plane transverse to this beam direction. So, and since momentum is a conserved quantity, it means that after the collision, when the protons have disappeared and instead we have produced new particles, the sum of the momenta of all these new particles that we produce should also be zero then in the transverse plane. So, and if we see something that isn't zero, it means that something invisible was produced and carried away this missing momentum. Of course, if we only produce dark matter and nothing else, then we would just see nothing. So there would be nothing no imbalance to be detected. So we need to exploit the fact that dark matter can be produced together with standard model particles. And then you would see these visible particles, and you would see that they have a net transverse momentum that isn't zero, and you could infer then that these dark matter particles had been produced and left without carrying away some of the momentum. And here you see a sketch of this, where you have something visible on one side of the detector and nothing on the other side, this missing momentum. And here is actually an event display showing exactly this, where you here have this visible object, in this case, a shower of hadrons that comes from the production of a quark or a gluon. And then on the other side, nothing. So this dashed red line is just, an arrow that says nothing. It's just painted on there. It's not a signal in the detector. And this object here on top actually has a transverse momentum of 1.9 tera electron volts, so it's quite energetic. So this could be the production of dark matter, but it could also be a background process from the standard model. For instance, there could be a Z boson produced going downwards here that decay to 2 neutrinos that are also invisible to our detector. So it's not enough to just see one of these events and say we have discovered dark matter. We need to see if we see more of them than what we expect from standard model processes. And actually, so far, we have not seen an excess of these types of events. So instead, we use these data that we have collected so far to place limits on, for instance, the masses of dark matter particles and the coupling to standard model particles. And here's just one example of that from the CMS collaboration, where on the x-axis you have the dark matter mass, and on the y-axis you have basically the probability of dark matter interacting with, in this case, a proton. And you can see that there are different lines here that are exclusion limits from CMS then. So everything above here would be excluded by CMS within these contours. And then you have these green ones that are limits from other type of experiments. And I just want to point out, since Frank showed this axion plot, that here he had also a similar plot where the masses in his plot were like below an electron volt, significantly below an electron volt. And here you can see it's more like giga electron volts. So these are much heavier dark matter candidates than the axion. But you can see that the LHC experiments cover this kind of, in this plot, low mass region, where the other experiments are not so strong. So these are complementary to other dark matter searches, but unfortunately, no signal so far. Another thing that we can exploit in the search for dark matter is the fact that the dark matter indeed has mass. That's something we know about it. And we know that the particles in the standard model get their mass from interactions with the Higgs boson. So if the dark matter also gets its mass from Higgs boson interactions, then we would expect to see Higgs bosons once in a while decaying into dark matter particles that would then be invisible to us. So we would call those invisible Higgs decays. And we have searched for such events, and we have not observed any significant amount of them. So therefore, again, we can use these kinds of data to place limits on these dark matter particles that the Higgs boson could have decayed to, but so far we haven't seen it. And again, here you can see some limits, in this case from the ATLAS experiment, where we set limits again in the kind of 1 GeV region of dark matter masses. these were just a couple of examples of how we search for dark matter. This is a nice illustration from the CMS experiment where they show all the different types of dark matter hypotheses that these LHC experiments are searching for. You can see it's a very rich phenomenology and a very rich field that, you can dive into if you look at this paper. Another thing that I want to briefly touch upon before I close is this question of the imbalance between the matter and antimatter, because our theories does suggest that the universe was indeed created with equal amounts of matter and antimatter, far back. And if that was the case, then this matter and antimatter over time should have met each other and annihilated and left only energy or photons behind. So that is not compatible with us living in a universe made of matter. So what made this matter survive? So this is something that people have thought about, and the hypothesis is that there must have been some surplus of baryons, so these particles made of quarks, over the antibaryons, so the ones made out of antiquarks, developing over time. And this is a phenomenon referred to as baryogenesis, because these kind of baryons are, born in some sense. They live happily ever after, not annihilating with their anti-baryon partners. And Andrei Sakharov in the 60s wrote down these 3 necessary conditions for having this baryogenesis taking place. So the first 2 of these have to do with that you need processes essentially that differs between matter and antimatter, so that you can develop some kind of net plus of matter over antimatter. The last process here has to do with the fact that you don't want that process to happen in reverse, because then you would kind of take away the imbalance that you have created. And for that not to happen, you need some kind of part of the universe history where it was out of thermal equilibrium, so that the processes cannot happen in both directions with similar probabilities. So I will only be able to dip my toe into this, and I will talk a little bit about 2 of these 3 conditions, namely the last 2. So CP violation, so this kind of difference between matter and antimatter, has been known to exist since the 60s, actually. So it's something we know exists in the standard model, but we have too little of it to explain the matter-antimatter asymmetry that we see in the universe. The LHCb experiment at CERN is working very actively on looking for new sources of CP violation, new processes that make this difference between matter and antimatter. So until very recently, these kinds of processes had only been seen in meson decays, so processes that involve particles containing a quark and an antiquark. But now for the first time, 2025, so only a few months ago, they observed it in processes that contain baryons, so particles consisting of 3 quarks or 3 antiquarks. So you can read more about that in this Nature paper here, but this was really a big step forward in the kind of CP violation search. Another place where CP violation in principle could exist is in the lepton sector. This has not yet been observed, but there are quite a few exciting experiments coming up that will probe this. So maybe we will see some hints of this in the future. This thermal equilibrium, or this out of equilibrium third Sakharov condition, could be related to the Higgs boson, because the Higgs boson has actually undergone a phase transition, or the Higgs field has undergone a phase transition that could have been out of equilibrium in the early universe. Because when the universe was very young, the Higgs field was actually at 0, and the potential had this kind of boring quadratic shape that you see here. But about a picosecond or so after the Big Bang, the potential changed shape, and the Higgs field transitioned into a non-zero ground state. And it's at this point in time when the elementary particles actually got their masses. Before that, they were massless. And this could have been a turbulent process that was out of equilibrium. And if that was the case or not depends on the shape of this potential. And the shape of this potential is linked to how probabilities for the Higgs boson to interact with itself. And this is something we can actually measure at the LHC through a production of pairs of Higgs bosons. And if this mechanism is as in the standard model, it will take us, basically another 15 years or so to see it. But if it is different from what the standard model predicts, we could see it even earlier. So this is something that is very exciting coming up from the LHC in the next few years. So In the near future, the LHC will actually continue to take data. So right now we're towards the end of run 3, and we will soon go into a long shutdown to prepare for upgrades to have more data per second collected. So in this high luminosity phase of the LHC, as it's called, we will collect 10 times more data per second, and that program will start in the 2030 and extend all the way until 2041. So when it closes, then the LHC in 2041, and it will have been running for 30 years, and it will actually leave an enormous legacy in the particle physics community. But we're already thinking about the next step. So CERN's proposal for the next flagship collider is the Future Circular Collider, which will be a 90.7 kilometer long accelerator with 4 experiments. And in the first phase, it will collide electrons with positrons to study the Higgs boson in detail. And in the second phase, it would collide protons, just like the LHC, but at a much higher energy, about 6 times the LHC energy. And currently, there is a feasibility study that is being wrapped up, and the decision about whether or not this accelerator will be built will be taken in 2028. And my personal goal is to see this collider taking data before I retire. So with that, I stop. Thank you very much.
Thank you, Sara. It was a great talk and overview, and in the interest of time, we will just continue to the next speaker. So, Oksana Iarygina, please introduce yourself and your talk, and give your talk. Thank you.
Yes, thank you. Oh, sorry, I will share my screen. Yes. So, can you see it?
Yes, it's good.
So hello everyone, my name is Oksana and I'm postdoctoral researcher at Nordita. So I'm really happy to be here today with you and talk about gravitational waves from the early universe. So every story about gravitational waves starts with Albert Einstein, about his theory of general relativity that has been discovered in 1915. So what it tells us is that essentially our space is not something static, it's a dynamical substance. So it can move, it can stretch, and its dynamic depends on the matter that is present in our universe, on the light and the energy. So you can see here as an example how the massive bodies can bend the geometry of the space. If to add a little bit of movement to these massive bodies in our universe, you can see a nice illustration of what happens when this massive body moves. So this blue grid illustrates our space-time, 3-dimensional space. And when the planet or a star moves in this grid of the space, it bends the space. So when there are 2 bodies move in the space, you can already see that these ripples in the space-time would create gravitational waves. Let's move forward and see what happens if these 2 objects actually spiral each other and then at some point merge. So you can see that this spiraling movement is getting accelerated. It accelerates even more. And then boom, we have the creation of a gravitational wave. And such a gravitational wave has been detected for the first time in 2015, exactly 100 years after the Einstein prediction. So the first detection called GV 150914, so you should read it at 14th of September 2015. And it has been detected by LIGO-Virgo collaboration. And how it works is that we have 2-arm detectors. So essentially it's an interferometer, and the length of this arm of an interferometer is 4 kilometers. So we have a laser that splits into 2 beams, and then it goes back and creates interference pattern. So if there is no gravitational waves, then the interferometer is calibrated in such a way that we don't see any signal in the interferometer because of a destructive interference of the waves. But if the gravitational wave from such as in spiral movement of 2 bodies moves through the Earth, then it can stretch the one arm of the detector and squeeze another arm of the detector such that interference picture is changed and we start to see the signal. And the first signal has been detected from the black hole mergers. So you can see the signal that has been detected. So here it's just like a white noise. There is just this small gravitational waves from just in spiral movement of the black holes. Then we can see the increase of a signal. And then when we had the peak in the gravitational wave production, we have this merging phase, or when the new black hole is forming down. And the curious part is that we can actually hear the gravitational wave in the way that the frequency of the signal can be transformed into the frequency of the sound waves. And here I have an illustration of a sound of the very first detection of gravitational waves. So you will hear two different signals. So the one signal is just original frequency that has been detected by LIGO and Virgo. And the second frequency is just elevated a little bit, 30% elevated, just to adapt it to our human ear. So let's listen to gravitational wave. So this beeping sounds like whoop, it corresponds to the elevated frequency that has been adapted. But nevertheless, it's very exciting to hear actually such an exciting events that happen in the early universe. And if you're excited about it, there is even an application that you can download to your mobile phone. It's called gravitational wave events that would send you a notification whenever a gravitational wave has been detected that passes through Earth, so you can be up to date whenever there is a gravitational wave around. Okay, and such gravitational wave detection has been really, really important for the early universe. So this plot shows the different black holes that has been discovered through this gravitational wave measurements. So the blue red circles, they correspond to the black holes that has been detected. The orange circles corresponds to the neutron stars, and pink and yellow, they correspond to black holes and neutron stars that has been detected through the optical methods through telescopes. The gravitational waves that descend from merging objects like to black holes or to neutron stars, we call astrophysical sources of gravitational waves. So this is the recent image from the James Webb Telescope that shows the image of our universe. And this the bright objects are not stars; they are individual galaxies. That's just amazing how much detailed we can see our universe nowadays. So talking about energy scales, these astrophysical sources of gravitational waves are located somewhere here. So we currently estimate the age of our universe to be 13.8 billion years. And these black hole mergers could originate from 5-7 billion years ago. So we could see it, we can say that we can see sometimes these events by optical telescopes, but there are some events that are completely inaccessible to us through the optical waves. And these events are somehow hidden from us because all the light that we can see, it comes from the cosmic microwave background. Then photons have decoupled and they travel freely through the universe. So we can still observe this very old and relic photons through the optical way. However, the very first stages of the evolution of our universe are completely hidden from us. However, the gravitational waves can travel freely, and they open for us this new avenue to study the very first moments of our universe evolution. So talking about energies, my talk is about really high energies, about inflation, phase transitions that go so much as to 1016 GeV. And just to advertise that a lot of research is done both at Nordita and Stockholm University in different branches of this universe timeline. So I'll start with inflation. So what is inflation? Inflation is an exponential exponential growth of our universe. It's just a rapid, accelerated expansion that happened at the very first fraction of a second, starting from the evolution of our universe. So I have a diagram that shows the radius of our universe with respect to time. And you can see that inflation is happening somewhere here. So the time scale is about 10 to minus 35 seconds after the start of our universe evolution. And essentially what happens is that inflation starts at the very, very early universe when there are quantum fluctuations of our space. And these quantum fluctuations are getting stretched to cosmological scales that provides a seed for the structure that we can see now for the galaxies, planets, and stars that we observe now in our universe. And so we can learn a lot about inflation from the cosmic microwave background. As I mentioned, it's the relic light, the very first photons that we know about. And the temperature nowadays of these photons is 2.75 Kelvin. And what's important is that this radiation has some inhomogeneities. So it's inhomogeneous up to 10 to minus 5 degree. And you can see these different dots here. So the dots with the red color represents the places where it's with the hotter density fluctuations, and the blue regions show the colder density fluctuations. So inflation predicts exactly how these fluctuations and the degree of inhomogeneity of these fluctuations of the cosmic microwave background. So what we can study in the cosmic microwave background is its statistics. So we can study the power spectrum. It's just a correlation, 2-point correlation function between two different points in the cosmic microwave background, and also the so-called bispectrum, which is a 3-point correlation function. And the power spectrum can be parameterized by an amplitude and the so-called spectral index. So similarly, from inflation, we expect stochastic gravitational wave background. So we haven't detected it yet, but this is just an example that is expected from inflation. So you can see it's really noisy signal. So what we can study only statistical properties of the signal. But the important information about this is the amplitude of the signal that can constrain the parameter, the so-called tensor to scalar ratio, which is the ratio between amplitude of the tensor modes to the amplitude of the scalar modes that we have seen on the previous transparency about the cosmic microwave background. And this gives us a lot of information for the so-called N sub S R plot. So this is very recent result from the Atacama telescope collaboration. And this plot, it constrains a lot of models that are coming from inflation. So we can constrain the amount of gravitational wave that has been produced during inflation, as well as the spectral tilt in the power spectrum, this N sub S index. So typically, the signal from inflation is expected to be really small. So this is the plot that shows the spectral energy density of the gravitational wave background with respect to the frequency. And there is some bunch of experiments that some of them are running and some of them are still planned for the future. And I will get back to this in a couple of minutes. But the message is that the amplitude of the gravitational wave is this black dashed line is really small. However, there are some models that can increase the amplitude of the gravitational waves, and some model relates to the models to the axion that Frank was discussing in his very first talk. And there is a huge research at Nordita currently, and not only at Nordita, about axion inflation, how axion inflation can produce observable signal in the upcoming observations. So, but not only inflation can produce gravitational waves. Let's look at some other sources that can also produce interesting signatures. So the first one is cosmological phase transitions. It has also been described briefly in the previous talks. So the cosmological phase transitions, it could be QCD phase transition or electroweak phase transition, and there are several ways how it can go. So the first way is that the phase transition can be really violent. It can be first order phase transition. Then the new phase, the new favorable vacuum cannot form simultaneously all over the place, but instead it would nucleate through the bubbles. And another way is when we have a smooth second order transition or a crossover. So here you can see an example of an effective potential. So this particular example is for Higgs, but it can be some other field. So the idea is that at high temperatures, we have some potential, but then when the universe cools down, in the first order phase transition, we start to see some potential barrier or this bump, such that the field cannot transition smoothly, but it rather has to go through the quantum or thermal tunneling to a new vacuum. However, in the second order phase transition, the transition is smooth. So the QCD phase transition as well as electroweak phase transition, as far as we know now, are crossovers. So we do not expect the formation of the gravitational waves from the smooth phase transition. However, as Sara mentioned in the previous talk, to solve the matter-antimatter asymmetry in our universe, there are some proposals that this phase transition have actually be rather first order. So if it happens that there was a first order phase transition in our universe, that we will definitely see it through gravitational waves. And how it works? So you can imagine that when the field transfers from the old vacuum to the new vacuum, it starts to form bubbles. So it's very similar when the water boils in the kettle, when there is a phase transition from water to the vapor. So here is something similar. We have a false vacuum state outside of a bubble and the true vacuum state inside the bubble. And then these bubbles expand, they collide, and they produce gravitational waves. So I have some illustration how it works. You can see a formation of a bubbles of a true vacuum state. This bubble grow, they penetrate the space, and then they collide. So whenever there are these collisions of the bubbles, our space-time is getting disturbed or perturbed, and we would see the we would see gravitational waves. Okay, another possible source of gravitational waves, so-called cosmic strings. So cosmic strings are one-dimensional topological defects, and they could form through some symmetry break and phase transitions. And there is that because of the topology, the energy just got stuck along such a long tube. It's like a cosmic spaghetti that could also interact and bend. And whenever there are collisions of the cosmic strings, there is also production of a gravitational wave signal. So, and this is expected gravitational wave signals from these three different sources that I just covered. So here you can see the energy density of the gravitational waves, and this is the frequency. So inflation produces very low signal in the very simple scenarios. Of course, as I mentioned, it can be changed in the more complicated interactions. And this peak corresponds to the first order phase transition signal when we have the collision of the bubbles. And the blue curve corresponds to the gravitational wave signal from the cosmic strings. Okay, the other sources that I don't have much time to go into detail, but nevertheless, I would like to mention them. So one of them is reheating after inflation. So when inflation ends, we have a phase of the particle production when there are bursts of particle production that could be go exponentially. There could be some violent tachyonic instabilities that can also produce gravitational waves. Another way is primordial black holes. So when primordial black hole forms, there is the huge overdensities that collapse into the black holes, and such a collapse would also produce ripples in our space-time that we should see. And also, there is a possibility for the different turbulent processes that magnetohydrodynamic can describe very well. So finally, how can we detect primordial gravitational waves? So I mentioned before, for the very first detection of the gravitational waves, it has been done by LIGO Virgo-Kagra collaboration. So, and it has been done by the Earth-based interferometers. So there are interferometers with the arm lengths of 4 kilometers that can probe the frequency from 10 hertz until roughly 5 kilohertz. And the sensitivity is just mind-blowing of this detector. So you can imagine that when the gravitational wave passes through the Earth, so these interferometers are sensitive to displacements that are less than 1 to 10,000 of the diameter of a proton. It's just amazing how much sensitive it is. The next upgrade of such Earth-based interferometers is planned for 2035. So it's called Einstein telescope. So the arm length of this interferometer is going to be extended from 4 kilometers to 10 kilometers, and there is some increase in the frequency as well. And it will be sensitive to displacements up to 10 to minus 22 meters. And another further update or improvement in the sensitivity is going to be done by the Cosmic Explorer, which will have arm lengths of 40 kilometers, which is also planned to be based on Earth in 2035 or 2040. There are also space-based interferometers that are planned in the near future, in the 2035 roughly. So one of them is called LISA, which stands for Laser Interferometer Space Antenna. So LISA has now arm lengths of not 40 kilometers, but 2.5 million kilometers in between, because it is based not on Earth, it's based in space. So there is such a freedom or luxury to do that. And it's going to probe the frequency ranges from 10 to minus 4 to 1 hertz, roughly. So it will be orbiting together with Earth on the same orbit. So you can see here an example. So there is Sun, there is Earth, and LISA should follow the Earth. And it should look something like this. So you can see on the video how it's planned to be. All right, and the LISA is going to detect, or it's going to be sensitive to multiple sources that I've described. So this is a quite complicated plot, but let me tell you about this. So this is again the plot for the energy density of the gravitational waves with respect to frequency. So these two lines, black and gray, are sensitivities of the LISA detector. And orange curve corresponds to the cosmic string signature from the cosmic spaghetti. So the green curve corresponds to the phase transitions from the collision of the bubbles. And this one corresponds to the stellar black hole binaries, and the blue curve corresponds to the galactic foreground noise. So indeed, like what we covered before in this presentation is this orange and green curve mostly. So it would be really exciting that the LISA would detect some primordial gravitational wave signal from such an exciting event. Also, another gravitational wave detector that is planned in space is called LightBird. So it's going to measure the polarization of the cosmic microwave background. So the idea is that without gravitational waves, our light has only E-mode polarization. You can see how it looks like here. But if the gravitational wave travels through the space, then gravitational waves, it tilts the polarization of the radic light by 45 degrees. So we are supposed to see this curly B-mode polarization signal. And its signal is expected to look something like this. So this is an old plot from the BICEP collaboration that first claimed that there is a detection of the B-mode polarization, but however, unfortunately, it turned out to be just some dust signal in our galaxy. But nevertheless, it's really exciting to measure this B-mode signal and understand its connection to gravitational wave from inflation. Okay, another
Oksana,
observatory.
We need to, the time is running short now.
Yes, I'm almost done. So the next one is just Simon's observatory that is also measuring cosmic microwave background. So another experiment that can measure gravitational wave is called pulsar timing arrays. So you can imagine the rotating neutron stars in our space, and the rotating neutron stars, they emit periodic radio frequency pulses, and these pulses can be detected by the telescopes on our Earth. So whenever there is a gravitational waves, this periodic pulses is getting distorted. So then we can infer from them the information about possible gravitational wave signal, and this signal can be either astrophysical, coming from the black holes or neutron stars, or it can be also from the early universe. But however, the main point is that we cannot just rely on one frequency here. We should look at the much wider range of frequency in order to distinguish between different sources that produce the signal from the early universe. So the take-home message is that really there is a bright future in gravitational wave detections, and if the gravitational wave has been produced not so far from us, from the objects like black holes or some in spiral merger objects, then it usually has a short wavelengths and millisecond wavelengths, or if it's produced at the very early universe, then the wavelength is of the age of the universe, and we just cannot detect it by ground-based interferometers in our ears. So I'll stop at this, and thank you very much for your attention.
Thank you very much, Oksana, and it was a great talk, and I'm also happy to announce that you were awarded a Vetenskapsrådet starting grant for the research you described here during your talk. So congratulations from all of us.
That's amazing. Thank you very much for this news.
Yeah,
Wow.
so it's very good. So, and yes, but let's continue now with Oliver and the final talk.
Hello, good day, everybody. Can you hear and see me?
Yes, we see you, and
I hope you can furthermore see my slides.
Yep, it's working fine. Thank you.
Right. Ready to start? Okay, yeah, hello everybody. My name is Oliver Schlotterer. I'm an associate professor at Uppsala University, and my research evolves around the mathematics of fundamental interactions. So thanks a lot for having me. I gratefully accepted the kind invitation to tell you about some links between particle physics and gravity from a gadget known as scattering amplitudes. Whoops. Yes. Okay, so on this intro slide, I believe I can be somewhat brief, given that the other speakers have nicely settled the stage. So you heard a lot about the frameworks for our fundamental interactions of nature. From Oksana, you heard more about general relativity, which is the theoretical framework to take care of gravitational force. So there, the key idea is geometry, that gravitational force is a matter of curvature of space-time. And now let's look at the three remaining interactions, electromagnetism and strong and weak force. So there we heard from Sara about the standard model of particle physics, and the theoretical umbrella taking care of all that is known as quantum field theory, or a specific variant, namely with the gauge principle, gauged quantum field theory. And there the key idea in quantum field theory is that both matter and interactions are composed of fundamental quanta or particles. Say when electrons exert electromagnetic force, then they exchange messenger particles such as a photon. Okay, so conceptually, general relativity looks miles apart from quantum field theory, and they operate on completely different length or energy scales. So it looks like I have a hard time linking them. But let me try nevertheless. Yeah, so the different scales on which they operate, one signal of that is that the experiments look like falling into very different scale sectors, either the microscopic scale, which is probed at particle colliders, or the astronomical scale of where gravitational wave experiments take place. Now, a link of them from the theorist's point of view goes through the notion of scattering amplitudes. So these are mathematical quantities that theorists compute to make predictions for experiments, actually for both particle physics and gravity. So scattering amplitudes line up with what I just told you about electrons exchanging a photon. This is how electromagnetic force is exerted. And think of this more generally, that also gravitational force can be exerted by exchanging, for instance, gravitons. And now scattering amplitudes follow the mantra of quantum mechanics that you should sum over all possible histories. So not only can a single messenger particle be exchanged, but maybe multiple of them. So you can draw an increasing wealth of diagrams with more and more loops. And this simply means there can be multiple exchanges. And here I kept it simple to an example from QED, namely electrons throwing around photons. But you can also do this to other ingredients of the standard model, or also in the gravitational case. Now, there are rules in quantum field theory to assign mathematical expressions to these pretty pictures. And these mathematical expressions will eventually translate into cross-sections. It's a longer pipeline to do that, but yeah, it's the computation of amplitudes which, at the end of the day, computes a probability. And you see, I need to draw more and more diagrams with more and more loops. And if we have finite time to compute, we stop with some number of loops. And depending on which loop order we stop, this limits the precision of the theoretical prediction. And there is impressive progress with experimental prediction. So theorists are challenged to catch up, to make theoretical predictions at a comparable accuracy, which means that we have to compute amplitudes at pretty high loop order. Now, it might be easier for you to see the notion of amplitude connect with particle physics. I mean, this is just taking along the key premise of quantum field theory, that we are exchanging messenger particles. But also in gravity, or specifically predictions for gravitational wave experiments, line up with scattering amplitudes. So here, the rough idea is to approximate, for instance, black holes, or maybe neutron stars, through point particles, which have a certain mass, clearly a mass at completely different scale than the particles we observe at LHC. But let's say the formalism and this notion of Feynman diagrams carries over. Now, if you want to make a prediction for the gravitational wave template in black hole mergers, you also draw Feynman diagrams as if you were to do a scattering amplitude for a LHC process. And I was lazy and didn't tell you what kind of coupling constants or expansion parameters are in the game. Here it's the Newton constant, namely that diagrams with more loops correspond to more powers of the Newton constant. Okay, now this is the rough framework and the rules according to which we do scattering amplitude computations. But how difficult are they? And in gravity, you have a difficulty just by the size of the mathematical expressions or the number of terms. So there are Feynman rules in both particle physics and gravity, which assign, say, to each vertex a specific mathematical expression. And in gravity, they are damn long. So already 2,800 terms for a 4-vertex. And this gets even worse when you count the number of terms in full-fledged Feynman diagrams. Say, if we are ambitious in our precision and want to take the 2-loop diagrams along, then if each vertex and internal line has multiple terms, then this single 2-loop diagram is in the order of magnitude of 10 to the 18 terms. So this is just one diagram, and needless to say, if you have sufficiently many loops and legs, then also the sheer counting of diagrams is a rough ride. So we have a kind of combinatorial issue if we want to do gravity at a high precision level. And a mitigation for that is at the same time the first link between gravity and particle physics that I want to highlight. Namely, these combinatorially challenging gravity amplitudes have a double copy structure. So in a loose sense, I can get them from squares of much simpler amplitudes, namely in gauge theory, where the counting of terms is much, much, much milder. So that's both conceptually and practically interesting that there's a double copy link between particle physics and gravity. So I'm using this slide already as an outline. So there is later a chapter with a second link between particle physics and gravity, which is of more mathematical nature. These Feynman diagrams and amplitudes, they sometimes represent integrals in a mathematical sense. So whenever there's a loop, you have to integrate over some momentum circulating in the loop. So these are high-dimensional integrals, which are probably more difficult than those that you have seen in analysis classes. And here, a mitigation strategy uses some modern mathematical insights from algebraic geometry and number theory. And that is also a universal business to both particle physics and gravity, and therefore the second link that I want to talk about. Okay, so this is the outline. Let's go into this double copy story, why I dare to claim that perturbative gravity resembles a square of gauge theory portions. So here is a lightning dip into string theory. I don't want to present string theory as a tentative candidate of quantum gravity, but instead I want to use it as an inspirational machine to tell us about links between gravity and particle physics that may not be completely obvious from GR and quantum field theory. Namely, the graviton, namely the messenger particle for gravity, comes from vibration modes of closed strings, whereas the photon and the other gauge bosons of quantum field theory interactions, they come from open strings. Okay, there are additionally some infinite numbers of vibration modes, but you don't need to know much about them for the purpose of this talk. So if open strings gives home to gauge theory and closed strings give home to gravity, well, then we can just compute the corresponding amplitudes in string theory. And once we are done, take the length scale of these strings to 0. Okay, so let's take a closer look of how that proceeds. And the first incarnation of double copy is for the states. Namely, gravity, as I said, comes from the vibration modes of closed strings. And when you let a closed string vibrate, you may have wiggles that go clockwise or counterclockwise around the closed string, left and right moving wave ripples. That's gravity. And the degrees of freedom in terms of these ripples are the same as, well, in the tensor product of two open strings. Say the open string will have some boundary condition to the endpoint. So one open string takes care of the left mover, and you need a second open string taking care of the right mover. So this is how a graviton can be viewed loosely as a double copy of two photons, or if you prefer the strong force, two gluons. And the same double copy has an incarnation at the level of the amplitudes. I can do closed string amplitude computations, and they have something to do with squares of open string computations in string theory. But now we send the length parameter to 0 once we are done evaluating string amplitudes as a function of that. And we recover Feynman diagrams. We recover QFT amplitudes coming from the open string, and we recover the amplitudes of perturbative gravity coming from the closed string. And since the parental formalism has double copy structure, so we'll have the Feynman diagram expansions we find in gauge theory / gravity. So this is to give you a rough idea why string theory inspires such a double copy organization scheme of gravitational amplitudes, loosely as squares of gauge theory building blocks. Now, two important disclaimers are in order about the practicalities of that. The first one is, I mentioned integrals that we need to do in Feynman diagrams whenever there's a loop. So you have to integrate over some internal momenta, and that's something that the double copy doesn't do for you. What does have double copy is the integrand with respect to the loop momenta. So if in gravity, I try to assemble the loop integrand, so that's the place where I complained that there might be 10 to the 18 terms. then the 10 to the 18 are in truth just a square of something simpler in gauge theory, which has considerably less terms, and which string theory helps you to simplify further. Okay, so here this is what you do in the comfortable situation where you look at particular gravitational theories and particular gauge theories that are directly reached from point particle limit of strings. But perhaps you have a very specific process in mind for standard model physics, for black hole merger. So it's not clear whether the process you have in mind is directly the L string to zero limit of a string theory process. And it doesn't need to be the case. This double copy paradigm for gravity has a life on its own, way beyond string theory. So I told you the string theory story to build up intuition and to tell you how simple instances have a very rigorous underpinning. But this double copy paradigm works extremely flexibly. So many cases far beyond far beyond the reach of a verbatim string theory calculation. Yeah, so some of the Uppsala colleagues are leading figures on that. So there is a famous review which was honored with the Frontiers of Science Award. And there are local colleagues, Marco Chiadaroli and Henrik Johansson, among the authors who are sitting a few doors away from me. Okay, and let me be clear. Given the flexibility of this double copy paradigm, then you can really apply that to processes, say, of gravitational wave radiation for specific black holes, which don't need to line up verbatim with a string theory setting. Getting this gravitational radiation as a square of a much simpler calculation of radiation in gauge theory. Okay, so this concludes the first link, particle physics gravity, via double copy at the level of scattering amplitudes and their loop integrand. Now let's move on to integrals. So as I mentioned, whenever there's a loop in a Feynman diagram, there is a loop momentum that you're supposed to integrate. And this requires integration techniques which you usually don't learn at high school or also not at undergraduate university studies. You need a lot of mathematical machinery, including, for instance, special functions. I guess more people in the chat know the exponential and the sine function and the logarithm. And then after the logarithm are many more jazzed up versions known as multiple polylogarithms. This is what nails subset of the Feynman diagrams coming from one loop diagrams. But already for the second loop order, still moderately low level of precision where we would like to calculate, we don't even know the complete set of special functions. Which generalizations of polylogarithms do you the favor of catching all two-loop Feynman diagrams? Yeah, embarrassingly, we don't have an answer to that yet, even though it's so pressing to have them for experiments, both in particle physics and in gravity. And the way out of that is to pay more attention to geometry. Namely, that Feynman integrals have a hidden geometry, which you cannot read off from the graph, but which is a beautiful organizing principle of the special functions therein. So you can, loosely speaking, associate these multiple polylogarithms to the Riemann sphere. If you look at their definition as integrals over rational functions, then you can see that they arise from integration on a two-dimensional sphere. And now, once we go beyond the comfort zone of one-loop diagrams, we encounter more complicated geometry, like in this two-loop example, where we have to deal with a two-dimensional donut-shaped torus as the hidden geometry of this two-loop graph. And there are actually many, many further difficult two-loop graphs which have the same torus geometry. So the Feynman diagrams may look very different. The physical processes they describe too also look somewhat different, but nevertheless, they have a unified geometry. So the torus knows it all about this multitude of diagrams. And the torus geometry is not the end of the rope. I mean, eventually we aim at very high precision for our theoretical predictions, and we will encounter more adventurous geometries. So if we insist on staying two-dimensional, but allow for more holes in the torus, you get what we call a Riemann surface. And these are the bread and butter of string theorists. So if you evaluate a string amplitude, you have to deal with Riemann surfaces, have some points on them for external states, integrate over possible geometries. So string amplitudes teach you about how to integrate on these two-dimensional surfaces, which is a substantial window into the mathematics of Feynman integrals. And with two-dimensional geometries, we're still not at the end of the rope. So as we go to sufficiently high precision level in gravity and gauge amplitudes, we will also encounter higher dimensional geometries. So some examples are known under the name of K3 or Calabi-Yau varieties. Here is a desperate attempt to draw them. And yeah, you need to understand the algebraic geometry of these Calabi-Yaus in K3 to fluently do Feynman integrals at a higher loop order. And if you want me to pinpoint big and pressing problems in the field, one huge unsolved problem is to have a simple map between the Feynman graph for the integral and the underlying geometry or the function space you need to solve and approximate the integral. Yeah, and for gravitational wave matters, for instance, there has been a recent paper in the Nature journal by some of my friends. So they found Calabi-Yau geometry, certain 6 real-dimensional geometries that take care of very high post-Minkowskian orders. If you're looking at the binary black hole in spiral and want to have precision calculations, say, from deflection angle and alike observables. So it's important to have a good mathematical handle on Calabi-Yaus to come up with precision predictions for black hole merger. Okay, so then to conclude, I tried to introduce the notion of scattering amplitudes as a bridge between theory and experiment that universally applies to our 4 fundamental interactions, both gravity in the GR framework and to the strong, weak, and electromagnetic forces in the QFT framework and the standard model. So a first link was inspired by string theory, namely that gravitational amplitudes have a double copy structure, can be somehow factorized into bits and pieces from gauge theory amplitudes. So gravitational force versus the 3 others. And then a second link was more mathematical in nature, namely this concerned the Feynman integrals, the bridge that we all have to cross if we want to make precision predictions, let it be for gravitational wave experiments or for particle colliders. And here there were some exciting geometries, including sphere, torus, or higher dimensional Calabi-Yau varieties that are governing the mathematical structure of our predictions. Okay, that's it, what I wanted to say. Thanks a lot for your attention.
Thank you so much, Oliver. So now we can let all the panelists turn on their videos and we will have a joint discussion of about 20 minutes based on these talks. So I would like to start by asking to connect immediately to Oliver's talk. So these new exciting techniques to compute amplitudes, can they be used then already now, for example, at CERN or Oksana's early universe gravitational wave scattering experiments, Sara? Or maybe something about the axions too, Frank? But Sara, could you start with that? Do you think you can use Oliver's techniques here at CERN, at LHC?
I think I should let Oliver answer that. I mean, I can maybe say that in principle, the precision of theoretical calculations is going to be a big challenge in particle physics going forward, right? Because with this future circular collider that I told you about, if it gets built, then we will start to have extremely good precision on the experimental side, and it's going to be a challenge for the theory to match this. So I hope that, you know, Oliver's work will eventually be useful, but maybe it's a bit more in the future. I think for now, people are more thinking about just cranking the perturbative calculations, you know, to higher loop orders. But Oliver can comment, I'm sure.
Yeah, thank you, Sara, for the opportunity to clarify more. I mentioned there's a very long pipeline from the calculation of the scattering amplitude at the microscopic level And then the elementary particles will organize themselves into jets and many more things that are eventually measured. So scattering amplitudes are one piece of the pipeline, which clearly has a bottleneck, but there is great work from many, many further communities needed to really run into a prediction for a probability in the signal as it is measured.
Yeah, thank you. So Oksana and Frank, do you have any thoughts about this, how to join forces between the experimental side and these kind of theoretical developments like the ones that Oliver are exploring here?
Well, I think it has to be viewed in a larger context. I mean, there are many kinds of difficult calculations that need to be done to relate modern theory and experiment. And calculating higher loops in highly symmetric theories, it just is one piece of it, but using supercomputers in different ways, machine learning, there are many, many approaches to this challenge of taking our fundamental knowledge and using it to explain complex phenomena.
Yeah, thank you. Oksana, do you have any thoughts about this?
Yeah, I can add that I think there is a beauty in theoretical approaches because precisely they create different links between different experiments. So, for instance, like Sara described, the correction to the Higgs potential, they could be very much linked to the early universe and behavior of different particles and also interaction with the Higgs. And this is what theoretical frameworks could tell us about and provide the links between completely different things that we would otherwise didn't expect.
Right. Yeah. Thank you. And Sara, you mentioned looking very, very far into the future. You mentioned that if we compare it to from 1930s, this has been an increase in energy levels that we can reach in these particle collider experiments by a factor of 1 million. But when we saw your plot, it was also leveling out a little bit. So will we be able to reach another factor of 1 million in the year 2130, or are we reaching our limit here?
But you're right that the curve has flattened out in the last kind of 10, 20 years. And I think it's an indication of the fact that we need some kind of technology leap to go forward.
Yeah.
So far what we're doing is just scaling up the technologies we're already having. We're refining, how we can build magnets and so on. But things that are in the pipeline but not really mature enough at the moment is, for instance, plasma wave field accelerators, which would give you a much higher electric field gradient, so you can accelerate faster over shorter distances. We also have exciting things like muon colliders on the horizon that potentially could be technologically mature in maybe a few tens of years. So I think there's hope, but for sure we need much more research on accelerator development in order to get to the next technologies.
Anyone else want to chip in on that? Yeah. No. Okay, very good. So I have a question for Frank. So you developed this idea of the accent, and if we look now at these talks, we see that this concept of the Mexican hat potential, it appears a lot in this high energy physics experiment. We have it in axion, we have it in the Higgs boson, also in some inflationary models it appears.
Phase transitions. Right?
Phase transitions, exactly. So will all of our fundamental progress the coming years be about understanding the Mexican hat potential and its implications?
No, we have to. Again, it's an important part of the picture, but it's not the whole thing. I mean, maybe the context in which the Mexican hat typically arises is in the discussion of symmetry breaking. So we like to have laws. It's not a matter of what we like. Late nature seems to like laws with a tremendous amount of symmetry. And as you go to shorter distances and probe more basic interactions, you find that the description has even more symmetry than is evident in the world as we see it in more ordinary circumstances. So relating equations with high symmetry to a world with lower symmetry is it has been a revelation of our improving understanding of the world. That is very central. But there are other, and the idea that there are fields that are responsible for symmetry breaking and maybe have energy landscapes that look like Mexican hats is one way of hiding symmetry, but there are other ways. There are the axion is associated with the symmetry that's of a special class, where it's a symmetry of the classical but not of the quantum theory. So it's broken by quantum theory. We have anomaly. That's anomalies. We also have symmetries that are asymptotic, that only appear at high energies and are spoiled by the scale invariance of QCD and other field theories is an example of that. We have symmetries that are hidden by confinement. So there are many ways of hiding symmetry. Very interesting. A lot of physics is devoted. A big part of modern physics is devoted to that question, and the Mexican hat is one key idea, but there are many. Right.
Okay, great. So I would like to bounce one part of your talk to a question to Oliver relating to this about symmetries, because Frank, you mentioned in your talk that there was this idea that all the forces, fundamental forces, would meet at very high energies, but to realize that to see that kind of meeting point, you needed supersymmetry. But supersymmetry has become a little bit not as fashionable anymore, since we didn't detect any supersymmetric particles.
No, it's very disappointing.
Very disappointing, yes. But I would like to ask Oliver in relationship to that, because what you hinted at in your talk was that there are actually very deep mathematical equivalences or parallels between gravity and particle physics. So does that imply that they kind of come from some joint underlying framework or not?
Yeah, so thanks for the opportunity to stress that. There was no supersymmetry requirement, neither in part 2 nor in part 3 of my talk. So this double copy paradigm, maybe it was for the first time seen in a supersymmetric string theory, but its range of validity goes far beyond. So you don't need any supersymmetry in the game to make that happen. By now, there is a big web of different particle and gravity theories connected by different double copies. Most of them being non-supersymmetric. I think even for spontaneous symmetry breaking, there are double copy paradigms where you break different types of symmetries on gravity and gauge theory side. That touches upon work by my local colleagues, Henrik Johansson, Marco Chiodoroli. And yeah, it's likewise for the Feynman integrals. So now I'm jumping to the mathematical side of my talk. So there I wanted to universally talk about all the Feynman integrals that you can get in some local quantum field theory. Let it be the toy theory of phi to the fourth that you study in your first quantum field theory class, or really standard model with gluons exchanging all various types of bosons, Möller scattering, W bosons in the loop. So in all of these situations, you have to eventually cross the same bridge and have a handle on these Feynman integrals. So no need for supersymmetry whatsoever.
Yeah, okay, thank you. Anyone wants to comment on that, or should we move on?
Well, I just want to say that the circumstantial evidence for low energy supersymmetry based on unification of couplings, to me, is extremely suggestive. But that calculation is kind of logarithmic in scale. So whereas for a theorist, the logarithm, if you're off by one or two factors in the logarithm, it doesn't matter. But for the experiment, it's a very big deal. So I believe one of the important motivations for pushing ahead at CERN, as Sara mentioned, I think is to see whether this picture is still correct. And we just haven't looked hard enough yet.
So there could be surprises in wait there for us.
Well, it would be a surprise that's not a surprise, I guess. Yeah. That's right.
Non-surprising surprises. Okay, that sounds great. And Oksana, one thing I thought about from your talk was that if we look at the early days of particle physics, then the detection was, for example, on photographic plates, bubble chamber photographs and so on, you could really see a particle there, and then you had a little bit noisy background. But today, to extract these kind of signals, you have a very noisy foreground, and then you need to use statistical methods to extract a signal from that. So how sure can we be when we find a signal that it's not a statistical fluke, that it's actually a real physical signal? What do you think about that?
Yeah, thanks for this question. So one way is, of course, cross-correlation between different signals. So this has been done by LIGO, Virgo, Gabra. So the original gravitational wave signal has been detected in the US, and LIGO and Virgo detectors have been located and are located on the opposite sides of the US. So it's not by an accident. It's because it's nice to cross-correlate the signal. So whenever there is some suspicion for a signal in one detector, it can be checked at another detector. So now there are 3 detectors, with the third one, I think, in Italy. Of course, it's much more complicated with space-based interferometers like LISA, as I described in my slide. So it's a huge interferometer, 2.5 million kilometers, but we don't know what can be cross-correlated with, right? So there are no second interferometer in space that we could cross-correlate. So the detection is really for the detection, it's really crucial to understand what are the noise models for the LISA, and how can we extract correctly the noise from the signal. Indeed, like I think a lot of people are working on this right now, and it's still a huge question.
Is there any techniques that you use for your experiment that you could learn more? I mean, is there anything, for example, what they do at CERN with their statistical techniques that you could use, and vice versa?
So I'm not working with experimental data. I'm working more on the theoretical side. So, but I think, yeah. So I know that so there is a galaxy background noise, of course. So the people first of all extract this galaxy background noise from the stochastic gravitational wave signal. That's the first way to do, and then there should be some calibration of the noise that has been done.
Yeah, thank you. And Sara?
Jump in. I mean, there are, of course, lots of cross talk between the different disciplines of experimental physics, right? So, everything from the very detailed statistical kind of tools that you use in order to turn the experimental results into statistical claims. I mean, that, likelihood ratios and whatnot, but also, different, techniques in order to estimate background from the data, with control regions, also now with kind of inference when, machine learning is more and more being exploited in all sorts of fields. So, yeah. I mean, of course, the specifics are different, but the tools are very much the same. So there's lots to learn from each other.
Yeah. We have a few minutes left before we end this seminar, and I thought we could just have a final round of just free, spontaneous thoughts when you heard the other people's talks. Was there anything in particular that you picked up on or felt inspired by? And let's start from the beginning, so we go through in the same list that we have the speakers, so the speaker list. So if we start with Frank, some final comments.
Well, I think there are a lot of frontiers of things you could call high energy physics, much ground to explore, a lot to love, and I had to be very selective in what I mentioned, and that was good. That going through that exercise was an inspiration to figure the thing that I think the new tools that are coming out for data analysis using machine learning, for new instruments with gravitational waves, new methods of computation, those are all going to produce a lot of excellent work, and the problems out there are major problems where particle physics and high energy physics has, I think, been so successful that it's difficult to improve on where we are now. But the questions, on the other hand, the questions we can address are really profound and and inspiring with the nature of the dark matter, the dark energy, unification of the forces, and the quantum nature of gravity. All these things are for the future. So we have problems, we have tools, and we can be proud of our legacy, but there's much more to be done.
Thank you, Sara.
So maybe one thing that was really inspiring was to see how, all the speakers today really addressed similar questions from very different angles, right? So I think it's clear that, we have a lot in common, and there's lots of work to be done by many, many people. And I really think, following up on what Frank said, that we have learned a lot from the past, but and it can be a bit frustrating now as maybe a particle physicist to fail so miserably in cracking a hole in the standard model. But, my personal belief, at least, is that, there's lots and lots of knowledge that we still need to gather, right? I mean, if you try to learn from past experience, we have only a glimpse of, what the universe could reveal to us. So, we should just keep on looking with the tools that we have available and try to address these questions. I'm sure there are interesting surprises to come.
Thank you, Oksana.
Yes, I completely agree with Sara and Frank that there is a lot of in common between the different talks. And I think the important point is just talk to each other, talk to different people from different subfields, so we can learn a lot from each other, and we can gain some techniques from each other. And if we just do like a lot of cross collaborative work, then we could advance science even more. So I think the future is in big collaborations, because it's just enormously big data sets are coming and enormously big experiments. So it's just impossible to do it by like a single scientist. So the collaborations are really important, and we need just to join our forces to explore our universe.
Thank you. And finally, Oliver.
I couldn't agree more with the previous speakers. Importance of collaboration, importance of being in continuous dialogue about how we have different viewpoints in the core similar ideas. And I think it's communication in between countries, it's communication in between communities, what drives progress. I think it was envisioned in the preparatory emails, whether or not we talk about that. Centers like Nordita do a fantastic job in bringing people together, offering a platform where one can really exchange in person. Programs, sometimes a few days, sometimes multiple weeks. I think this is so essential, the possibility to have such meetings according to proposals that are submitted to Nordita and elsewhere. Then having extended period where people get together, are not within their local duties of their home institutes, and really can talk freely with good time resources. This is so crucial, has been highly important to me personally in on my scientific development. And I hope we can all work together to have also in the future a continuum of such events and meetings, programs, as broad as possible, and integrating different viewpoints.
During the span of my own career, when I was a graduate student, there were sort of high walls separating cosmology from condensed matter physics, from particle physics. Those were just different things with different techniques and different subject matters. Now those walls are obliterated. Understanding of how nature works, that really is also fun for a theorist, because it means you can wander freely through this larger landscape.
Okay, very good. And that's a great note to end on. So thank you to all the panelists who joined this Quantum Leap seminar, and in particular also
Yeah.
So thank you, everyone, and I hope you see you all who was attending this seminar also at the next Quantum Leap event. So thank you and bye.
Bye now.
Jonas, big
Bye.
congrats to the organizers.
Thank you. Thank you.
Well done. Well done. Yeah.
Thank you.